Okay, this is the M1 paper from May 2022. Question number 5, and as you can see by looking at it, this is going to be a moments question. What you'll also notice is that I've started the diagram down there just to save myself a little bit of time. I always think it's important to redraw these diagrams out rather than trying to put various different bits of information on the printed diagram, simply because when I'm taking my moments later, I want it to be really clear where my lengths are. So it takes a couple of minutes to do the extra diagram, but I think it's worthwhile in the end. So what have we got? We've got, excuse me, A, B, C and D here. And it says that this is a uniform rod of length 5 and mass 5 kilograms. So I know then that I've got a 5G force acting there, where this is going to be 2.5 and this is going to be 2.5. I'm not going to leave those two lengths on because I've got more information, but that's in my head already. It tells me I've got a pivot point, a pivot point at C there. So I'm going to have a reaction force straight away of RC that I label it, and a reaction force then of RD there. Now, sometimes on other questions, they'll tell me that one's double the other one, but here we've just got two distinct different variables, which is absolutely fine. We'll sort that out when we're doing the question. In the question, it says I've got a mass of 10, so 10G acting at A, and I've got a mass of mg, acting at B. And again, in the question, it tells me that that length there is 1 meter. And it tells me that this length here is 2 meters. So because I said earlier that this 5G is acting in the middle, acting at 2.5, then that means that this length here must be 0.5 meters. And finally, that length there must be 1.5 meters. So now that's a really good diagram to start off from when I'm trying to do all my working out, simply because all the lengths are nice and clear there as we're going through. Now, we've got a number of different possibilities for what we can do in terms of attacking these questions. We can resolve vertically, which is actually what I'm going to do first, and I'm going to get that those two forces going up are in equilibrium with those forces going down. So straight away, that's going to give me a relationship between RC and RD. Let's tell the examiner what we're doing. So resolve vertically means that RC plus RD are in equilibrium, so they're the same as 10G plus 5G plus mg. I can just tidy that up, not a lot, just one simple step to make that 15G plus mg there. So that's going to be useful later on. I've got a relationship now between RC and RD. What that means is if I work out RC, then I can get RD by rearranging it, or if I get RD, then I can work out RC by rearranging it. Okay, what are the questions? I haven't really looked at the question properly. Question says, find RC. Find RC. So if I'm doing this then, hopefully, as you know, we can take moments anywhere at all. We can take moments about there, about there, about there, about there, about there. It doesn't matter where we take moments. But if I want to get RC, really what I want to try and do is to eliminate RD from my moments question. So if I take moments about that point there, the whole idea is that then the RD disappears because it would be RD times the distance away from D, which would be 0. So the RD will disappear if I decide, so this is what I'm going to decide to do, to take moments about C. I could just as easily have taken moments about D. Take moments about D. Take moments about D because I want the D to disappear. I could have, as I said, take moments about C there if I was trying to work out what RD is. Right, so when we're doing this, taking moments about D, this is the whole point about this diagram now. It's nice and clear. So I'm going to do, when I'm working out my moments, I'm going to do RC times 2 meters plus mg times 2 meters. Both of those are going clockwise. and they'll be equal to the 0.5 times 5g there, and what's going to work out to be 10 times, looking at that length there, that length is going to be 3, isn't it? Because 1 plus 1.5 plus 0.5. Okay, let's do that now, taking a little bit of time to explain it to you. So RC times 2, mg times 2 is equal to, it's in equilibrium, so clockwise and anti-clockwise are equal to each other, 10g times 3 and 5g times 0.5. So I want to try and get what RC is. Let's just tidy this up, not take too long over it. So 2RC plus 2mg is equal to, that works out to be 32.5 g. So RC, let's do it. 2RC is 32.5 g minus 2mg, and RC then is half of that. So RC, I'm just going to half each bit actually, is 16.25 g minus mg. So that's part A done, nice and easy. We've worked out what RC is in terms of m. Now if I want to work out RD, I could do exactly the same thing and just take moments about C instead. So that is one option that you can do. But what I'm going to do, because I've already done this bit up here, I'm just going to use that information just a little bit quicker. Well, it's not necessarily quicker, but it's just something that I prefer to do. So for part B, if I'm going to work out RD, I'm going to say from equation 1, notice that I labelled it before, I'm going to get RD works out to be 15g plus mg minus RC. So RD works out to be 15g plus mg minus 16.25g plus mg there. So RD works out to be, and this is just algebra now, shouldn't take you too many steps to be able to do this. That works out to be 2mg minus 1.25g. So I found RC and I found RD. One of them by taking moments, one of them by resolving vertically. So I like the fact that I've done two different methods there. And then part C, this is the slightly harder part, but you just need to use your common sense here when we're looking at this. I'll explain it first and then we'll actually do it. So it says find the range of possible values of m. Now remember, m is this mass that I've got going on here. So if we're in equilibrium, then what we've got with this rod is that this rod is not going to start moving in any way. But the limits would be RC and RD. They both have to be greater than or equal to naught, okay? And actually it's the equals naught part that's the more important part. I could have RD working out to be equal to naught, in which case this whole thing here would be pivoting around about this point, RC. It would just start to move, or I could have a situation where this whole thing was just going to start trying to move around about the point RD. So at those two possibilities, and you should have seen those from previous questions, we can either have RC working out to be equal to naught, or we can have RD working out to be equal to naught. And at those two situations, they're going to be the extremes. They're going to be the possibilities. So having explained that to you, now let's explain that to the examiner. I'm going to say for a range of values of m, RC and and RD both have to be greater than or equal to naught, and I'm going to assume, let's do RC first of all. So if RC is greater than or equal to naught, we get 16.25g minus mg is greater than or equal to naught. And obviously we can cancel the g's out there. rearrange it, I'm going to get 16.25 is greater than or equal to m, or rather, to put it so it's nice and easy to understand, m has to be less than or equal to 16.25. Now let's do RD being greater than or equal to 0. So I get 2mg minus 1.25g is greater than or equal to 0. Do the same thing again about cancelling the g's. I'll get 2m greater than or equal to 1.25. I'll get m greater than or equal to 0.625. So that gives me my final answer then, that m has to be between 16.25 and 0.625 for the rod to remain in equilibrium. And at those two values, it's either, this rod here is either just going to start tilting about D but not actually move, or just start tilting about C. When it starts to tilt about C, RD will be equal to 0. When it starts to tilt about the other one, the opposite way round when we're doing them. Okay, hopefully that all makes sense.